force is caused by the gravitational force of the star. The purpose of the second part of this assignment is to determine the initial velocity required for the spaceship to get close enough to the black hole without crashing and then leave the system. This is also done using GlowScript and uses Newton's second law to predict its motion. Moving on to the fundamental principles for the first assignment. Here we look into Newton's second law and note that F net is equal to the sum of parallel forces and the perpendicular forces. F net is also equal to dp over dt, which you can see down below. We also have the gravitational force here and the MBH, which we will use further down. Moving to the computational model. Here, we generated individual values using my seed value, which is my email, and then here are the given conditions. We have the mass of the star and the time interval between imported data points. As we move on, we see that we plug in the equation P is equal to ME, MV, which is the momentum formula, and we use the F net formula, which is F net equal to dp over dt, and then F net is equal to sum of parallel forces and perpendicular forces, and then finally this all is used to find mass of the black hole. Next is the computational model. And I have the results displayed here. We have F net, which is equal to 7.56575 e to the power 28. This is the sum of 1.25714 e to the power 28 and 7.46734 e to the power 28. And as you can see, this curves around and then moves. Moving to part 2 of the assignment, we have the fundamental principles. Here we also use Newton's second law, which is F net is equal to dp over dt, gravitational force, where F grav is equal to g m1 m2 over r square, unit force, r hat. And then we have the velocity update formula and position update formula, which changes with each iteration and loop that we go through with the computational model. Here's the code for part 2. We kept everything the same. We inputted the values from our last part, which is bh.m, and here it's 9.01861 e to the power 33, and then we have our constants, which we do not change, and that's basically it. And then here's how the curve looks when I run the program. It's able to curve perfectly around the system and not be sucked into or thrown out like the pink line is. And the calculations are finished after 60 minutes, and the ship is now 1.55401 e to the power 34 away from the event horizon of the black hole. So, moving on to the interpretation of part 2. Here is the net force and its parallel and perpendicular components, which are different from the rate of change of momentum and its parallel and perpendicular components. Using Newton's second law, we see that they are the same. The only difference is a matter of calculations. The net force required the mass of the black hole, while the change of momentum can be found through observing the object's position, velocity, and momentum in relation to time. What if, instead of entering, we enter into an orbit around the black hole? To do that, we need to edit the next 2 lines, which says we need to edit the initial velocity of the ship. But the only constraint that we have is that the spaceship cannot move faster than light, because that is impossible. If we continue changing these, then we can manipulate the results and get a different result for part 2. Thank you so much and have a nice day.